In this video lecture, I will provide a few definitions relevant to current and voltage sources. In particular, I will be discussing about ideal and independent sources. Before that, I will introduce the so-called passive sign convention. In electrical engineering, the passive sign convention is an arbitrary standard rule which is universally adopted by the electrical engineering community for defining the sign of electric power in an electric circuit. Based on this convention, the power flowing out of a circuit into an electrical component is positive, while the power flowing into the circuit from an electrical component is negative. Based on this convention, any passive component which consumes power, such as a light bulb, will have positive power dissipation, while any active component, a source of power such as an electric generator or a battery, will have negative power dissipation. This definition of the power is used also in computer circuit simulation programs, such as the so-called SPICE simulators. To comply with the passive sign convention, the direction of the voltage and of the current variables, which are used to calculate the power in a component, must have a certain relationship. The current variable must be defined so that positive current enters the positive voltage terminal of the device. By positive voltage terminal, we mean the terminal of the device which is at the higher potential. These directions, which are conventional directions, might be different from the directions of the actual current flow and voltage. This is quite an important point. The reference directions of the voltage and current variables, which can be assigned arbitrarily, must be distinguished from the direction of the actual voltage and current, which is only determined by the circuit. The idea of the passive sign convention is that if we assign the reference direction of the voltage and current variables in a component with the right relationship between them, then the power flow in passive components like resistors will come out positive, while the power flow in active components like voltage source, for example, which we will be discussing about later on, will come out negative. Therefore, choosing the relative direction of the voltage and the current variables in a component determines the direction of power flow that is considered as positive. Since we know that the power P is equal to the current times the voltage, by arbitrarily choosing the sign convention, we arbitrarily choose the relation between the current and the voltage, which provides a positive or a negative product, or a positive or negative power. According to the passive sign convention, the current variable is defined as positive if it enters the component through the terminal at the higher potential. So, the current flows from the terminal at the higher potential to the terminal at the lower potential, doing a work on the component, as occurs in passive components. As a consequence, power flowing into the component from the line is defined as positive. Based on this convention, the power variable represents the power dissipated in the component. Therefore, active components, for example, power sources, will feature a negative power flow. Passive components, or loads, will feature a positive power flow. Another possible choice is that of adopting active sign convention. In the case of active sign convention, the current variable is defined as positive if it exits the component through the terminal at the higher potential. In this case, the current flows from the negative to the positive terminal of the component. So work is being done on the current and power flows out of the component. In the active sign convention, power flowing out of the component is therefore defined as positive. The power variable in this case represents the power produced by the component. Based on this convention, active components will feature a positive power flow, while passive components will feature a negative power flow. In general, sources are devices capable of providing power to an electronic circuit. Depending on the quantity they force into the circuit, they can be distinguished in voltage sources and current sources. An ideal voltage source is a device capable of maintaining at its output a certain voltage E, whatever current is required by the load to which the source is attached. In other words, an ideal voltage source can maintain across a component called load a given voltage E for which the source was purposely designed and provide to the same component the current it requires, whatever the value of the required current is. The voltage E is called the forced quantity, while the current I is called the resulting quantity. Note that according to the passive sign convention, the power dissipated by the load is positive, while according to the active sign convention, the power provided by the voltage source is positive. Also, if the load is a resistor with resistance R, then according to Ohm's law, the current I will be given by the voltage E across the resistor divided by R. Different symbols can be used to represent an ideal voltage source in an electronic circuit. For example, this symbol is used to represent a battery, which is a constant voltage source. These other symbols may be used to represent voltage signals, which are voltages changing with time. Note that in all the symbols, plus and minus signs are used to indicate which of the terminals is at a higher potential. To the same extent, an arrow could be used in place of the plus and minus signs, indicating the terminal at the higher potential. By the way, the second and the third symbol can also be used to indicate constant voltages, like the first one. In the last symbol on the right, the line inside the circle linking the two terminals of the voltage source is a mnemonic sign to remind us that when we switch off a voltage source, it becomes a short circuit. As we said, an ideal voltage source is a device which is capable of maintaining a given voltage E across a load independent of the current that the load requires. This is true whether the voltage generated is constant or changes in time. In the case of a voltage signal source, which is a voltage source that generates a voltage varying in time, the voltage forced into the circuit at any time instant is independent of the current that is required by the load at that instant. This plot shows the so-called voltage current characteristic of an ideal voltage source generating a constant voltage E. V represents the voltage forced by the voltage source, while I represents the current provided to the load. As you can see, the voltage is equal to E independent of the current I. In the case of a voltage signal source, the voltage generated by a voltage source can be represented as a function of time. At each particular time, the voltage current characteristic of this voltage signal source will feature a constant value of the voltage, the value assumed by the voltage at that particular time, independent of the current required by the load. An ideal current source is a device capable of forcing a given current A in a load with no dependence on the resulting voltage across the load itself. The current A is the forced quantity in this case, while the voltage V across the load is the resulting quantity. Note that, as in the case of the ideal voltage source, according to the passive sign convention, the power consumed in the load is positive, while according to the active sign convention, the power provided by the ideal current source is positive. If the load is a resistor, then according to Ohm's law, the voltage across the load will be equal to A, the current provided by the current source, times the resistance of the resistor. Different symbols can be used to represent an ideal current source in an electronic circuit. All of them can be used to represent a constant current source or a source generating a current changing with time. In all of them, the arrow, either inside the circle like in the first symbol or on the side, indicates the direction of the current. The horizontal line inside the circle in the second symbol is a mnemonic sign reminding us of the fact that when a current source is switched off, it behaves like an open circuit. We said that an ideal current source is a device capable of forcing a given current A in a load independent of the resulting voltage drop across the load itself. This is true whether the current is constant or changes in time. In the case of an ideal current source generating a current signal, so a current changing in time, the current forced into the load at any time instant is independent of the voltage drop resulting across the load at that instant. This plot represents the so-called current voltage characteristic of an ideal current source generating a constant current A. I is the current forced by the ideal current source into the load, while V is the voltage drop resulting across the load. In the plot, the current is always equal to A, independent of the value of the voltage V. In the case of a current signal source, the current generated by the source can be represented as a function of time. At each particular time, the current voltage characteristic of this current signal source will feature a constant value of the current corresponding to the value assumed by the current at that particular time, independent of the resulting voltage drop across the load. Voltage and current sources considered in this video lecture are called independent sources as the value of the voltage or of the current they generate is independent of any other voltage or current in the circuit they are used in. Also, dependent or controlled sources exist, where the generated voltage or current depends on the voltage in a node or the current in a branch of the circuit. Dependent voltage and current sources will be discussed in one of the next video lectures. To describe the operation of the ideal voltage source when it is switched off, I have used the expression short circuit. By short circuit, we mean an ideal conductor connecting 2 points or nodes in a circuit. The fact that the conductor is ideal implies that when the two nodes are connected together, the potential difference between them becomes zero. This is independent of the way we draw the conductor between the two nodes. Actually, switching a voltage source off means reducing the voltage generated by the source to zero, which is exactly what happens when we connect two nodes together with an ideal conductor. When instead I describe the operation of an ideal current source when it is switched off, I use the expression open circuit. By open circuit, we mean the absence of an electrical path between two nodes in a circuit. No current can flow from one node to another if there is no path between them. Actually, switching a current source off means exactly reducing to zero the current flowing between the two nodes connected by the current source itself. In the circuits we will be discussing in the next video lectures, we will use the notion of a ground reference or 0-volt reference, symbolized by this symbol. In an electronic circuit, this symbol represents the node of the circuit conventionally set at 0 volt. The potential in any point in the circuit can therefore be measured with respect to this point. Actually, we cannot say, for instance, that a node in a circuit has a potential of 10 volts unless the ground reference has been defined in that same circuit. That node will have a 10 volt potential difference with respect to the ground node. Consider, for example, this battery generating a potential difference of 2 volts between its two terminals. If we connect the negative terminal of the battery to ground, then we can say that the positive terminal is at a potential of 2 volts. Consider now two batteries, each generating a potential difference of 2 volts. Let us connect the positive terminal of one battery to the negative terminal of the other battery. This kind of connection is called a series connection. We will talk about that later on. The overall voltage difference across the series of these two batteries, which means the potential difference between the negative terminal of the bottom battery and the positive terminal of the top battery, will be 4 volts. If we connect the ground reference to the negative terminal of the bottom battery, then we can say that the common terminal of the two batteries is at a potential of 2 volts, by the positive terminal of the top battery is at a potential of 4 volts. Let's consider now again the same two batteries in the same series connection. And let's connect now the ground reference
to the common node of the two batteries. In this case, we can say that the negative terminal of the bottom battery is at a potential of minus 2 volts, while the positive terminal of the top battery is at a potential of 2 volts. The potential difference between the negative terminal of the bottom battery and the positive terminal of the top battery will still remain 4 volts. Consider now these two very simple circuits, including a battery and a resistor. The only difference between the two circuits is that in the one on the right, the negative terminal of the battery is connected to the ground reference. Nevertheless, the current I1 flowing through the resistor in the circuit on the left is the same as the current I2 flowing through the resistor in the circuit on the right. And these currents, I1 and I2, are both equal based on Ohm's law to the voltage across the resistor, 2 volts, which is forced by the battery, divided by 1 kilo, the resistance, which makes 2 milliamps. On the other hand, only for the circuit on the right, we can say that the positive terminal of the battery is at a potential of 2 volts.